Okay, so today we are doing directional derivatives. Okay. This is where this whole multivariable idea really starts to shine and becomes much, much more rich and subtle than single variable calculus. It's like, okay, what are we going to do? So in one variable, right, we have one independent variable, the x, and we have one dependent variable, y. And then what we do is we make graphs that relate x and y. Okay, so in a single variable, there's only one direction that you can change with respect to, right? You vary x, and your graph changes in some way. So you've got one notion of slope. Right? The slope of this tangent line is the slope of the curve at that point. But in multiple variables, we've got multiple directions of change. Right, so we can imagine changing in the x direction or changing in the y direction. Right, those give us those two notions. Right, the change as y varies or the change as x varies. So these are where you move parallel to the coordinate axes. Right, but as we move around in the world, we don't always go parallel to the coordinate axis. We don't always go forward and backward or left and right. Right, we can go in different directions. So to sort of draw a picture of this in the xy plane, right, we've got df dx, df dy, but there's other directions that we could travel in. We could go in this direction, right? We could talk about the slope as we move northeast, instead of just as the slope as we move east or the slope as we move north. Okay. So I want to recall the definitions of those partial derivatives, and we'll figure out how to generalize to arbitrary directions. So this is our, oh yes, question?
Is the x and y supposed to be switched?
Let's see. It's supposed to be switched. So this guy?
Yeah.
Right, yes, this thing. Right, so this is the x-axis, this is the y-axis. So I'd say this one's drawn kind of all right. Right, but if we look at this from above, right, so if we look down the z-axis, what do we see? Yeah, so we're looking down the z-axis. Yeah, right, good point. So this would be x and y. Yeah, good point. So the labeling here is not super duper critical. The idea is that we've just got two directions that we can measure change. Well, that's two of infinitely many. We can measure change in any direction. Okay. Okay, so here's our limit definition for going in the direction x. Right? So we're adding stuff to the x coordinate. And we can play the same game and define a rate of change in the y direction. Some notion of rate of change in the y direction because we're adding to the y coordinate. Okay. And now what we want to do is we want to generalize this to any direction. Right, so we'll take that direction and we'll add it in here. Wait. Okay. One moment. Is there something strange about this division before we move on? The top is definitely a number, but what's the bottom? It's a point, right? So we're dividing a number by a point. Kind of weird, right? You usually don't divide by points. So what we should do is we should make top and bottom into numbers. So we're going to make this into a length. Okay, so the top is change. Bottom is length. Okay, so now we've got number divided by number. We can do that division, that's fine. Okay, so what we have to do is we have to generalize this to arbitrary directions now. So the directional derivative of our function at a point AB in the direction V, we have to set up as a limit sort of in the same way. We'll call that the FDV. And now instead of moving parallel to the x-axis, parallel to the y-axis, we're going to move parallel to v. Okay, so we'll move in the direction v. So a couple weeks ago, a year ago, I have no idea. Someone asked, why do we make direction vectors have unit length? Right? What's the purpose of this unit length business? Okay, it's for this calculation here. So we make them have unit length so that when we calculate as follows, right? These ABs cancel out, and we're left with HV. And then the length of V is 1. Right? Directions are of unit length. Okay? So this is the place where we use directions are of unit length. If we didn't have the hypothesis of unit length, then this quantity would depend on the length of V somehow. It's not quite how we want it to work physically. Okay. The other nice thing about this equation is that it looks a lot like our first year derivative formula, right? It's change divided by h. So it matches with what we've seen before.